anyone can be an astronomer. All we need is nature's most abundant science lab, the open sky. Every time we look up at the sky, wondering what it contains, we're following the traditions of the earliest astronomers. But as time has advanced, so has the astronomer's eye. Today, it's not just looking through the eyepiece of an optical telescope, but finding newer ways to see. Not just answering old mysteries about the cosmos, but bringing up brand new questions of science. How do we observe the cosmos? The most obvious answer is with our eyes. But it isn't quite as simple. What's really going on? And is everything we see all there is in the universe? When we look at something, we receive light signals reflected from the object. The light is a phenomenon called electromagnetic radiation. Simply put, this radiation consists of waves which are described by frequency or the rate at which these waves go past you. They're also described by wavelengths or the shortest distance between their crests. The higher the frequency, the shorter the wavelength. The longer the wavelength, smaller the frequency. The human eye can see these waves only when their frequency is within the visible range of electromagnetic radiation. You can see the difference in frequencies within this range as color. But there is more to electromagnetic radiation than what our eyes can see. There are all kinds of different frequencies that electromagnetic waves can have, and together they are understood as the electromagnetic spectrum. The spectrum is arranged in decreasing order of frequency. So we have gamma rays, then X-rays, ultraviolet, optical, infrared rays, microwaves, and finally radio waves. While our eyes can only perceive optical frequencies, science and technology has allowed us to make observations in other frequencies as well. For example, there are many ways to observe the human body. You get one picture with your eyes, and you get quite another picture using X-ray light. If you were to picture the human body using infrared heat detectors, you'd get a completely different idea. If you combine all these pictures, you can put together a far more complete idea of what a human body is made of just by looking at it from a distance. Astronomers do the exact same thing when observing the cosmos.
You can learn complementary things about the universe by studying it in different wavelengths other than optical, because different objects tell different stories at different wavelengths. Optical happens to be one of them. Most of them emit in almost all parts of the electromagnetic spectrum.
Today, astronomers make observations in different bands of the electromagnetic spectrum, including ultraviolet, infrared, and gamma rays. Some of the most fascinating studies have been in the band of electromagnetic radiation known as radio. When we hear the word radio, most of us think of this. But this is simply a device that receives radio waves which are broadcast from a radio station and converts it to sound. Radio waves have very large wavelengths, from a few millimeters to a few meters. This means they have very small frequencies. Only thousands of millions to a few million waves pass by every second. In other words, thousands of megahertz to a few megahertz. So when you tune your transistor radio to a 91 megahertz station, it actually detects radio light at a frequency of 91 megahertz and converts it into sound for you. But what does this have to do with astronomy? For this, we need to imagine a very different type of radio receiver. One that can receive radio waves not from a radio station on Earth, but from objects in the universe that emit radio waves. This study of the universe in radio is known as radioastronomy. It's a field that began quite by accident in the early 20th century. Carl Jansky was an American engineer who was asked to investigate disturbances in the radio telegraph service across the Atlantic Ocean. While investigating these interferences, he discovered a kind of static noise that could only be explained as coming from somewhere in the Milky Way galaxy. In 1933, this discovery threw open the possibility of seeing the universe in a brand new light. If objects in the universe were radiating radio signals, then one could discover whole new objects and their properties just by building radio telescopes. By the 1960s, many groups around the world were studying the cosmos at radio frequencies. What would be revealed was a very different image of the universe, the radio universe. The 1960s also brought radioastronomy to India. The Tata Institute of Fundamental Research assembled a group of enthusiastic astronomers and engineers under Professor Govind Swarup. Professor Swarup had been energized by discoveries happening around the world in radioastronomy, and he wanted India to be a big part of it.
I was coming to India having 2 years in Australia, 7 years in the United States, to do something. Within 2 months' time after I returned to TFR, I got the idea there was a big controversy between Big Bang and steady state.
It was one of the central questions of science of its time. How did the universe begin? There were two prevalent theories that were vying for top spot. One was the Big Bang theory, explaining how the universe was born from an instantaneous expansion. The other was the steady state theory. That explained how the universe had always existed as it was, in a stable form. The evidence for this would come in large part from radioastronomy. Fortuitously, Govind Swarup had returned to India with 32 dish antennae donated by Australia.
Once I joined Tata Institute for Fundamental Research, those dishes were at Delhi. Baba got them to Bombay, and within 18 months, I set up the Kalyan radio telescope.
The Kalyan instrument was India's first radio telescope. It was designed to study the sun. It was succeeded by a bigger and more sophisticated one at Ooty in Tamil Nadu. The Ooty telescope was completely indigenous in design, and it gave Indian astronomers a distinct advantage by having one of the world's largest telescopes in their own backyard. It was used to determine the size of newly discovered distant radio sources, which could provide evidence for the Big Bang model. As 21st century physics reached into higher and higher energy paradigms, India's radio astronomy group's dreams became bigger and bigger.
We built the Ooty radio telescope. The group became famous, and then gave inspiration to do something bigger.
This is one of the 30 antennae that make up the GMRT, or Giant Meter Wave Radio Telescope, in Kodad, Maharashtra. Situated 80 kilometers away from the big city of Pune, it's earned its giant status by being one of the largest and most sensitive telescopes on the globe. These massive antennae are designed to receive extremely faint radio signals from faraway objects in our cosmos. The signals are received in the low frequency range of 150 to 1665 MHz. They are collected by parabolic dishes and captured by radio receivers. Next, these weak radio signals are amplified and carried away by optical fiber cables to supercomputing devices. This happens for each of the 30 antennae, which are spread across 25 kilometers. The information from individual dishes is mathematically combined, and finally, a complete image of the radio source emerges. And so, astronomers from around the country and world flock to the GMRT to study celestial objects that radiate light in radio frequencies.
It is rare really in the life of a developing nation that you build an innovative facility for basic sciences which is used by people from all over the world, just as a world class facility. Science is very competitive and you have to remain in the forefront. That means even to stay where you are, you have to keep running.
Indian astrophysicists are very much in the running, with research teams using the GMRT to answer a wide range of questions from the most complex to the most fundamental. What would the sky look like if we could see it in a radio band? This was the question asked by researchers at TIFR's National Centre for Radio Astrophysics, or NCRA. They decided to make a map of the full sky using the GMRT at very low frequencies of 150 MHz with a wavelength of 2 meters. They did this by imaging each part of the sky and then putting it all together. The TIFR GMRT Sky Survey is an atlas of the universe available to any astronomer interested in a 150 MHz view. It's quite different from the atlases made at higher frequencies with other telescopes.
What we are doing is surveying whole sky and putting out the science-ready images for everybody to be used in the world. So you can put out the coordinates of the sky on our web server and immediately you will get the images, you will get the catalogs, you can use those information directly into your papers.
If you have an optical astronomer and you're interested in some part of the sky, but you don't want to learn how to analyze radio data, radio techniques, you can just use our products and get a feel for what is that part of the sky looking at this band, So that way it gives a very useful information of the entire sky with a certain angular resolution and a certain sensitivity.
Today, the TIFR GMRT Sky Survey has nearly 2 million such radio sources. It's a tantalizing peephole offered into the radio universe, whose vast complexity is still being uncovered every day. In recent years, some of the most exciting work at the edge of radio astrophysics has been in the study of galaxies. Galaxies are massive colonies of stars, planets, and interstellar matter such as gas and dust. They are the large-scale building blocks of the universe. How they form, grow, behave, and evolve are questions that radio astronomers are very interested in. In India, some researchers are using the GMRT to study nearby dwarf galaxies. They hope to understand how these galaxies formed very long ago. They also hope to understand the mechanism by which these galaxies continue to form stars inside them. Today, physics theories point to something called dark matter as what makes up 27% of the universe or 85% of all matter. Astrophysicists try to piece together exactly how this happens inside galaxies.
So the stars we see, those beautiful galaxies we see, are actually the end product of huge dark matter conglomerates where gas, mainly in the form of hydrogen, is converted into stars. People don't really understand the last part, how gas falls into these dark matter halos, how it forms stars.
How does the GMRT help answer such questions? It has conducted one of the largest surveys of hydrogen gas distribution in the cosmos. By learning how hydrogen is arranged in galaxies, astrophysicists can piece together the mechanism of how the universe was built.
My work was to try to use that data and try to understand the relation between gas and star formation and try to see if that understanding can anyway help in understanding the bigger problems where what you are simulating is not really matching with what you are seeing in reality.
But results from radio telescopes don't look like what you'd expect from a usual telescope. Instead of images, you get numbers. These numbers are then processed in a computer program, which generates an image of the radio emissions.
We are looking at the signature of hydrogen in a small galaxy near our galaxy. So you can see slowly as you move away at different velocities, the position of the hydrogen is changing. What this corresponds to is that the hydrogen in that galaxy is in a huge disk, much more extended than the optical extent of that galaxy, and that hydrogen is rotating.
While some study nearby galaxies, others study faraway ones. Since the GMRT is such a large instrument, it is able to receive signals from very far away. The more distant the object, the longer the light takes to reach us. And so what we end up seeing is how it was much farther back in time. This gives astrophysicists a most unique opportunity to time travel. Today, researchers are studying the oldest galaxies to test physics' most dearly held laws, like fundamental constants. But what are fundamental constants? They are physical quantities whose value remains unchanged throughout nature and time. One of the most familiar fundamental constants is the speed of light. Denoted by the small letter c, its value is 299,792,458 meters per second in vacuum. This value remains constant throughout space and time. Why are fundamental constants like these so important? They are the glue that holds together our theories of the universe, and they explain the precise way our universe behaves. For example, you may have seen the speed of light in one of the most famous equations of our times. E is equal to mc square is an integral part of Einstein's special theory of relativity. It describes the proportional relationship between energy and mass in our universe.
The question we're trying to address is why are the fundamental constants of physics, like the speed of light, the electron charge, and so on, why are they what they are, and are they constant? That's an assumption in the standard model of particle physics. And so if you like, we are testing the current models of physics. So if we find evidence that the fundamental constants are different, that will show definitively that the current model of physics is incorrect.
To do this, astrophysicists train their radio telescopes towards some of the oldest objects in the sky, present closer to the Big Bang.
The light from them is taking like 1 billion years to get to us. So we've seen the universe as it was 10 billion years ago, for example. And the question that we are asking is, were the fundamental constants the same 10 billion years ago as they are in the lab today? I think we have tentative evidence of changes in one of these constants right now, which we are chasing up with Arecibo and GMRT.
If fundamental constants turn out to be variable, it would be a huge turning point in modern-day science. And it would push physicists to search for newer ways to explain how the universe works. The view from a radio telescope throws up many such expected and unexpected twists. One such twist is the pulsar, a unique lighthouse in the sky. Pulsars are neutron stars created after the supernova explosion of a massive star.
The size of a neutron star is actually the size of a city like Pune. And the density, if you can compare, you see that if you take a 1 sugar cube of neutron star and put the whole of humanity in another balance, then both of them sort of balance each other. So these are extreme objects. The surrounding of the neutron star is filled with electrons and positrons moving in these very extreme magnetic fields. Electron positrons in these strong magnetic fields are able to create very directed emission towards us. And since the star is rotating, this directed beam of emission passes your line of sight and you see a pulse of radiation.
Pulsars fascinate astrophysicists around the world, including those at NCRA. What are some of its biggest unsolved mysteries?
Pulsars are one of the objects emitting in the radio which is very fascinating to study because we know today why pulsar pulses, but we don't know why they shine.
Pulsars don't quite shine like the stars we're familiar with. Unlike the sun, they eject focused jets that gush out at speeds approaching the speed of light. At such high energies, conditions are unlike anything experienced on Earth. Therefore, pulsars often challenge our strongest principles of physics. This is why the discovery of pulsars is such a hot pursuit in radio astronomy. Most recently, NCRA has partnered in the discovery of a strange pulsar with rather chameleon-like behavior.
Within 1 second, this particular star is able to change its personality. That means the type of pulse, intensity and all that you see completely changes within a second, and then it has the ability to go back within that second. It's like this Dr. Jekyll and Mr. Hyde doing its own things. And what we don't know is that what exactly is the parameter on the star, what physics is going on such that it causes this sort of state change and exact state changes.
Every time a pulsar is discovered, it's great news for astronomers. This is especially true in the case of millisecond pulsars. As the name suggests, millisecond pulsars are pulsars which rotate around themselves hundreds of times every second. Compare that to our home planet Earth, which takes 24 hours to complete a rotation, and you can imagine just how fast a pulsar spins. But that's not all that's fascinating about them. It's all about how these pulsars are born. All pulsars are born when a neutron star begins to rotate rapidly, throwing out high-energy materials in extreme conditions. As the pulsar loses energy, it begins to slow down until it no longer sends out pulses. It has now entered a pulsar graveyard. But there's still hope of life if it's in a binary system. That is, if it has a companion. In this case, it begins to draw in matter and energy from it due to gravity. Re-energized, it gets a new lease of life. It begins to spin faster and faster until it is turned on again. It is now a millisecond pulsar. At NCRA, teams are studying special pulsar systems called Black Widow systems. Here, a millisecond pulsar is observed along with a companion in a binary system. But all is not as tranquil as it seems. This millisecond pulsar gradually destroys its companion by eating into its matter. And so, scientists closely study it, hoping it is the missing link to answer why some millisecond pulsars are found in binary while others are observed to be by themselves. Millisecond pulsars are much sought after discoveries in astrophysics. That is why GMRT's data analysis software and computing tools have been especially tailored to fine-tune the search.
So I have developed a software signal processing backend which is basically using the cluster computers where you sample the universe in a microsecond time order such that you can equip to find this kind of first millisecond objects.
Such innovations have allowed Indian astrophysicists to participate in an international pulsar search consortium with the American Fermi Telescope in space, which observes the universe in gamma rays.
Interestingly, that backend development actually resulted in such millisecond pulsar discovery, which we have from this Fermi follow-up under Pulsar Search Consortium.
Finding millisecond pulsars in the vast expanse of the universe is no easy task, but the benefits are many. They could help scientists understand the elusive gravitational waves. And as they are extremely stable in periodicity, they could be used as timekeepers, which can be even more accurate than atomic clocks.
they are like laboratories in the sky which is available to us. And we can then in principle apply this so-called known physics that we understand from our terrestrial experience to those systems, and then we see that if there is something new that's there that we have not thought about.
And so pulsars join the other inhabitants of the radio universe in challenging the frontiers of science. In this dance between astronomy and physics, they continually refine and renew our knowledge. Meanwhile, back on Earth, the concave bowls turn slowly, and radio telescopes reach far into the sky, patiently collecting feeble radio waves from the distant cosmos. They're revealing the deepest secrets of the universe. All we have to do is see differently. If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.